rewrite it in explicit form, it looks like this. And then in part B, I don't know which of these is easy to graph, but what does that shape make? Circle. From the original equation, how can you tell that's a circle? They're both squared and their coefficients are exactly the same. So we know it's a circle and the radius is 8. So draw a circle with radius 8. Try to put the center at the origin. Close enough. All right, so recognize your conics. Hey, that thing's a circle. Radius is 8. Origin's at the center. Do your best to draw a circle with a chord at the center. And then from the explicit form, we have the plus and the minus because the plus is the top half of the circle and the minus is the bottom half of the circle. And we need the plus or the minus to like get both halves of the circle because either one on its own doesn't do the whole thing. All right, for C, talk to us. All right, 1/2 that negative 1/2. So all that is D out. Times D in is times negative 2x. So what rule are we using here? Let's just chain rule. And then she threw 64 minus x squared down the stairs to make his exponent positive. And 1/2 negative 2x is negative x. That's fine. How do you go to here? So like this is good. You don't know how they got here? What if we look back up at the top here, where we like rewrote the function y equals something? What do you notice the y is the same as? That. See that? Oh. See that? Hey, that's y. Boom. Y. So that's the substitution that's going on. And we'll use that sort of idea in 47 when we go to simplify the second derivative. So if you didn't go here, that's fine. But that allows you to see that whether you do things explicitly or implicitly, the derivative really is the same, even if it looks different. This square root, that's the same as y, so you can replace it with y. In D, subtract the 2x, divide by the 2y, cancel out the 2's, you're done. And that's another way to express your derivative. So you can express your derivative in terms of just pure x, like this, or you can express it in terms of both x and y. The upside of using this version is that it's a simpler equation. The downside is that you need both x and y coordinates to be able to use it. Covers everything with 17. Do you guys have any follow-up questions with anything there? Oh, yes. A little bit, yeah. Not a ton, but it's not going to be. It's going to be there a little bit. Oh yeah, a little bit. No, you won't have to produce a graph of your own. There is a graph on here. I will give you the graph to help you kind of see it. So the whole quiz is 40 points. There's 4 of things like 13 and 15 of just, here's an equation, get the derivative, go. So there's 4 of those. There's a, here's an equation, let's analyze it. So like get the derivative, get the equation of the tangent line, get the equation of the normal line at the same point. I can give you the equation to say, get me the second derivative, like 47. I can give you an equation and say, get me the points where the tangent line is horizontal or where the tangent line is vertical, and that covers the whole rest of the quiz. So like all those kind of application problems where you get the derivative and then do something with it, whether it's finding a normal line equation or a tangent line equation, or where the tangent line is horizontal or vertical, or then getting a second derivative. That's pages 2 and 3. Yes. Some. Not a lot. But you got to know your trig function derivatives. You don't need to know your trig identities on this quiz, but you do need to know your trig function identities. Maybe as, oh, there already is a bonus. I was going to say maybe on the bonus, this is the back of the quiz. So it's only 3 pages again. So I was thinking maybe on the back I could say, for more extra credit, fill in all these blanks of like all these trig identities, but maybe. All right, any other comments with 17? All right, Ahmed, talk to us about 13. All right, so first times the derivative of the second. First is x. Derivative of the second piece is 0 plus the derivative of tangent secant squared of y. And then the derivative of the y thing is dy dx. And I'm writing this here because it's like not visible very long. So. And then what? Alright, so you distribute out the right side. So you distribute it as x through these, actually just drop the parentheses. This is x times secant squared y times dy dx. Is the dy dx inside the secant squared or not? It's not. So maybe it's a good idea to put parentheses around the secant squared of y to like make it clear the dy dx is not inside of that. And then here, don't need the parentheses anymore around that. 1 plus tangent y. There's nothing multiplying to it anymore. Then what do you do? Alright, so before you divide it, you actually also subtract the cosine x over here. So you picked up the whole dy dx term, moved it over here, and made it negative. So that's negative x secant squared y dy dx. And that equals this 1 plus tangent y is there, and you subtract it with cosine x. And then you divide all this stuff to get the dy dx by itself, and you're good. You get 1 plus tangent y minus cosine x with a negative x secant squared y. All right. So that is product rule. It's easy, again, to miss the product rule because it's easy to just kind of read right past x times stuff with y. But that is product rule because you're multiplying two functions and both parts involve a variable. You could have also distributed the x through and had x plus x tangent y, but then you'd still have to use your product rule on the x tangent y part. Any follow-up comments with 13? 15. Zelda.
Okay, so on the left side, you find the derivative of y, which is 1 divided by x. And on the right side, you use trig rule with product rule inside of it. So it's x divided by x plus y minus cosine xy.
So that's the derivative of the inside. And doing the derivative of the inside, you have to product rule. So that's first times the second plus the original first is 1 times, sorry, d first is 1 times second is y. And then derivative of sine is cosine of the inside stuff, so cosine of xy. Cool.
You don't really need the one of the dy dx. And then distributed the cosine xy to the x dy dx plus y. And then I moved all the things that had dy dx onto the left side. And you pull the dy dx out, and you have dy dx times 1 minus x cosine xy. It's all equal to y cosine xy. And then you just divide the 1 minus x cosine xy out. So you have dy dx
that's great. And again, this is obnoxious because at heart it's a chain rule problem, but you have product rule inside to deal with. You guys have any follow-up questions for 15? Yeah. Remember what the alternative is. Use the limit process with h approaches 0 on that thing. I don't know how you do that with y's, but that's the alternative. So if you're like, I don't like these shortcuts, yes you do. 47. Who are you? All right, Daphne, talk to us. All right, so now that you've got here, you're like, all right, I got to do the derivative again to get to the second derivative. So let's label that second derivative, d squared y over dx squared. Because that's a fraction, you got to do your quotient rule. So talk us through that. All right, pause. Any questions with setting up the quotient rule? And then, what do you do after that? Yeah. So if you stop right there with y squared minus x squared over y cubed, awesome. You get full points, as far as I'm concerned. But if you compare this back to the original equation, you say, hey, that's y squared minus x squared. The original equation was x squared minus y squared, so these are like opposites. And so she shows that by factoring out a -1. And so x squared minus y squared, you know that that's 36 from back at the beginning. So anywhere you see x squared minus y squared, you can replace that with 36. And that's what you did here to simplify this. If you stopped here and you didn't like turn the numerator into -36, fine. If you do that and you see that substitution that you can make, that's awesome. It's similar to what happened in 17 when Rose copied the key and say, hey, the square root of 64 minus x squared turned into y. I don't know why, but it did, because that square root is y. So when you see, like further back in a problem, an expression that you like already know, hey, there's a simpler version of that. That's just y. Or in this case, oh, that's just like 36. You're allowed to use that previous step or previous expression and do a substitution where it applies. So that's what's going on there at the end of 47. Any follow-up comments? All right. Whoops. Can you see that, Sabia? Oh, well. Just roll another die. 2 and 6. Rachel, kick the 6. 2 and 5. All right, so that was Daphne, that was Rose, Ahmed, Zelda. Thanks. Oh well. not blind and falling down person. Example 7. So let's go through that. Go through one more example. Those, like yesterday, if you watched the video or you were here, we went through just reminder of some basic implicit differentiation stuff. And then we also saw, I think, implicit differentiation in combination with chain rule, I think. And on Friday, we had already seen it in combination with product rule. And then today and yesterday, in the midst of doing a second derivative, we saw implicit differentiation in combination with a quotient rule. So today, we're going to do a little bit of review of the stuff that we did yesterday, and then hopefully get to whiteboards. Yes, ma'am. We're going to start notes, do example 7, example 8, and then whiteboards. So example 7, we've got this thing. We're going to analyze as much as we can out of that thing, and then we'll do example 8. Example 8 will be a messier equation, but less to do with it. So, what is that? Circle. And what's the radius of the circle? 5. So you can say, yeah, that's a circle of radius 5. Maybe it helps to have a picture. If you recognize what the thing is, draw the easy little sketch real quick if it's easy. Then, getting derivative, dy dx. Go ahead, you guys do that on your own for a minute and see if you can get dy dx for yourselves. Did we do example 6 yesterday? I can't remember. No, we didn't. I looked at example 6 and said, we've got other things that we can do are more worth our time. Leah, I didn't get to ask you homework. Homework? Yeah. Awesome. Thank you. And what rows was it? 2 and 5? Oh, man, picture quality on this camera is just really terrible. Yeah, 2y dy dx. All right, so x squared becomes what? 2x. Y squared becomes what? 2y dy dx. 25 becomes what? 0. Yeah, don't leave it as a 25. Then subtract over the 2x. Then divide by 2y. And what happens with your 2's? Cancel out. You're left with negative x over y. Compare that to the one I erased in the middle. And you'll see, hey, it's the same thing. Oops. So 17 in the middle that we did was a different circle, but it gives you the same derivative. Any circle you ever differentiate, as long as it's centered at the origin, will have negative x over y as its derivative, no matter what the radius is. So that's cool. So if you recognize, oh, that's a circle, you know the derivative is negative x over y, so long as it's centered at the origin. You can just write, oh, circle. Boom, derivative because circle. So that's fine. Just make sure it's actually a circle. Because if you see x squared minus y squared, that's not the derivative. I think it's the same thing, but positive. Now, once you got that, getting the second derivative is going to be very similar to what you saw in 47. So second derivative is what this symbol means, and when you differentiate the left side, it turns into that thing. So dy dx differentiated becomes this d squared y over dx squared thing. And to differentiate the right side, what do you have to do? Quotient rule, because it's a fraction. So this is now quotient rule. Low d high, what's low? What's d high? -1. Minus, thank you. Minus, don't mess that up. High d low, what's high? -x. What's d low? dy dx. Derivative of y is dy dx. All over low, which is y squared. So there's your setup of your quotient rule to get your second derivative. Then you kind of go through the numerator and see how you can clean this up. So you go, all right, y times -1, that's negative y. Not so bad. Negative x is positive x. All right. dy dx is negative x over y. So this is where you got to use a substitution and say, oh, the dy dx, don't leave it like that. We know what dy dx is. We just found it over here. So replace dy dx with what it really is, negative x over y, so that your derivative, the second derivative, can be in terms of just x and y and not in terms of dy dx at all. And then we've got a fraction within a fraction, so we have to do what? Yeah, we got it. Well, we can't just bop the y to the bottom because then that y will be dividing this y over here all of a sudden. So you got to be careful about that, and I recommend you multiply through by fancy 1. And what's our version of fancy 1 here? Y over y, because based on the denominator that you have to kill. So when you multiply through by fancy 1, the first half of the numerator becomes what? Negative y squared. X times negative x is negative x squared. The y's cancel out. That's why you multiplied by y, so you don't need to worry about that mini denominator. And downstairs we have y to the cubed. So we've got d squared y over dx squared. Now if you leave things like this, all well and good, that's fine. But you can simplify this more, which is useful if you have to get the second derivative at a point, which in chapter 3 is useful when we want to talk about the bendiness of the curve, which is what we call concavity. So in the numerator, how could you simplify this a little bit more? Take out a negative, so there's a GCF there of -1. And then you'd have y squared plus x squared left behind. And what do you know about y squared plus x squared? In this case, it's 25. Because x squared plus y squared is 25 back from the beginning. So at the very beginning, you're told x squared and y squared add up to 25. So y squared plus x squared is 25. Boom. So you can turn the second derivative into just -25 over y cubed. And so that way your second derivative depends only on your y coordinate, and it doesn't really care about the x. Yes?
Why is like when you write the second derivative, y is 2 and plus y and 2 half?
That's a good question. I should probably know that. I'm sure there's some like actual meaning behind it.
So if you wrote like d squared y over d squared x, that's wrong.
Technically, yes. It's a sort of wrong thing I could very well see myself not even noticing. Here's my theory. It's the second derivative, so we're squaring the derivative part on top. And with respect to x, so you know how like in position, velocity, acceleration? So like, say position is in feet, right? And time is in seconds. So then velocity is in feet per second. So the numerator stays the way it was. The y is still y, but now it's per time, it's per seconds. And then acceleration, the units are feet, still just y, that stays the same, but now it's per second squared. So like the x thing is getting squared. Maybe that's why. That's as good of an explanation as you're going to get out of me right now for that. Ask Google. Google probably knows. Any other questions? All right, so that's just, can you do the mechanics of getting your first and second derivatives, just working through your implicit differentiation and doing a substitution where necessary to get rid of a dy dx and maybe to simplify down at the end. In parts B through E, now we're like taking the derivative and using it to analyze the circle. So in part B, we want to write the equation of the tangent line to the curve at this point, -3, 4. So we have the point, the whole point, -3, 4. You don't need to find your y coordinate or anything. But what do we need to find to write the equation of the line? Slope. So to write the equation of the line, if you've already got the whole point, all you still need is a slope. So the slope is based on what? derivative, so f prime of x, but in this case we don't have f prime. Instead we have dy dx, but they amount to the same thing in terms of like what you do with them. So slopes of derivatives. In this case we're calling the derivative dy dx, and we're doing the derivative at negative 3 comma 4. So you take your derivative, negative x over y, and we'll have negative x is negative 3 over y is 4. So our slope is 3/4. Right? So that's the slope of your tangent line. Once you've got that, combine it with your point, and your tangent line is y minus 4 equals your slope 3/4 times x minus the x coordinate is x plus 3. So that's your tangent line to circle at negative 3 comma 4. Any comments to follow up on B? Coming up with the equation of a tangent line. In C, coming up with the equation of a normal line, what's the relationship of a normal line to a tangent line? They're what? I didn't hear actually. Perpendicular. So a normal line is perpendicular to a tangent line. Otherwise, everything's the same. So you already have the slope of the tangent line. Take that slope and make it perpendicular. So what's your perpendicular slope? Negative 4/3. And then you use that slope with the same point, because the normal line and tangent line will go through the same point, negative 3 comma 4, because we told you, go through negative 3 comma 4. Opposite reciprocal for perpendicular. Yeah, good to get that straightened out now. So yeah, perpendicular lines have opposite reciprocal slopes, not just reciprocal slopes. Because if you think about it, if you have like a line that's got a positive slope, and then the other line also has a positive slope, they can't be perpendicular. The only way you get perpendicular lines is if they're like going in opposite directions. So you have to have one line going up, the other one has to be going down, so they be perpendicular. So once you got your other slope for your normal line, same equation, y minus 4 equals slope is now negative 4/3 times x plus 3. So if you can get the equation of your tangent line, then by extension you can also get the equation of your normal line. Just take your tangent slope, flip it, make it negative, and now you're good to go. Any questions with either B or C, tangent and normal line equations? All right, part D, we want to find points on the curve where the tangent line is horizontal. So at the risk of like beating a dead horse here, what do we know about tangent lines or any lines that are horizontal? Slope is 0. So horizontal line means slope is 0. And what are slopes? Derivatives are slopes. So you say, hey, derivatives are slopes. dy dx equals m. What do you know about dy dx? Negative x over y. What do you know about your slope if your tangent line is horizontal? It's 0. So then you solve. So for this whole thing to equal 0, how do you solve it? Multiply y. You got negative x equals 0, so x equals 0. Now, is that a point? No. So we got to still find the point. What do we now do with this x equals 0? 0 pins for x back where? In the original equation. So we got to go back to the original equation. So x squared plus y squared equals 25. Plug 0 in there. And you hope and pray that we gave you an equation that is like actually kind of solvable. Not like maybe this thing. So you got 0 plus y squared equals 25. And so what's y going to be? Plus or minus 5. So don't forget. Remember, circles, you have 2 points for x equals 0. You got the point on the top and the point on the bottom of the curve. So you're going to have 2 points here, plus or minus 5. So all that is 0, comma, plus or minus 5 are points where the tangent line is horizontal. And if you look at your circle, what 2 points are those on the circle? So like, what special points on the circle are they? So 0, 5 is like right here. And 0, -5 is right here. So that's like, yeah, the heights. There's the maximum and the minimum points. When we get into chapter 3, if we get far enough, we're going to see that the maximum and minimum points on a curve almost always occur when the derivative is 0. So what we call those are critical points or critical values where you have a slope of 0 or a slope that's undefined. So that's why we also look at number E and see where is the tangent line going to be vertical. So when we have a tangent line that's vertical, what does that tell us about the slope? All right, so slope is undefined. And again, what is the same as slope? Derivative. So we say derivative equals slopes. And our derivative is negative x over y. We want that to be undefined now instead of equal to 0. In order for this whole fraction to be undefined, how does that happen? Yeah, you set the denominator equal to 0. So to make the derivative undefined, you always set the denominator of the derivative equal to 0. That's the equation you're going to make to solve. So tangent line horizontal, make your derivative equal 0. Tangent line vertical, make the denominator of your derivative equal 0. And then you do the same thing. You say, oh, solved it, y equals 0. Boom. Plug it into x squared plus y squared equals 25. And what's your x values? Yeah, so x, that's not a very good x, equals plus or minus 5. So your points are plus or minus 5 comma 0. Ta-da! So that's kind of a good problem because it covers all of our bases. It gets you practice with just basic implicit differentiation. It gets you to practice with quotient rule and implicit differentiation. It gets you to practice with substitution for dy dx as you get your second derivative. It gets you practice finding the tangent line equation and a normal line equation and thinking about when your tangent line is horizontal and thinking about when your tangent line is vertical. So on your actual quiz on Thursday, all of this would basically account for pages 2 and 3 of your quiz. But it'll be broken up over the course of like a couple of different equations. So you're not doing all of this with just one equation. So that if you screw something up on one of them, it's not necessarily affecting you down the line on like E or F number of parts for that problem. But you'll be doing these things with 2 or 3 different equations over the course of pages 2 and 3. Yeah. You're now assuming that it'll always be a circle. Right? So for a circle or an ellipse, yeah, you're absolutely right that the tangent line horizontal, those points are the top and the bottom of the circle, and the tangent line vertical are like the rightmost and leftmost points of the circle. But if I give you something that's not an ellipse or not a circle, that's not going to be, you might not look at it and say, oh, that's a circle. I might throw you like a circle kind of problem somewhere else, but not necessarily here. So don't just kind of like automatically rely on that assumption. That's really specific to circles. Any other questions? All right. One last thing and then whiteboards. Yes, ma'am. Yes, sir. Let me all pass. Go down. No names. Put that on there. All right, last one for us to go through together. We got x squared times the quantity x squared plus y squared equals y squared. So x squared times x squared plus y squared equals y squared. And if we leave it like that, the graph of this is an X chromosome. So, yeah, it looks like this. So you have vertical asymptotes at -1 and a +1. And then it looks like two parabolas, one facing up and one facing down. So yeah, it's X chromosome. Now that's if we leave things as they are. I would like to ramp up the difficulty level here just a tad. So instead of leaving it like this, we're going to slap an exponent there. Sound good? Not really. No, this is going to suck now. But this way, it's no longer that shape. I don't know what it's going to look like now. And also, the benefit of doing this is that from here on out, everything else will be comparatively easy. Because this now, what rule do you have to use on the left side? So I heard people say product rule, and I heard people say chain rule, and you're both right. So this is product rule. At heart, this is product rule. You have a first part times a second part. The reason I put the exponent here is to also give us chain rule and to prevent us from multiplying the x squared through and kind of simplifying things. I don't want you to do that. I want us to suffer. So we have a first part and we have a second part, and let's talk through this. And this is also for those of you who were not here yesterday to get the benefit of seeing how to avoid distributing stuff out fully. You guys remember that problem yesterday? The one where we like sort of distributed stuff out, but not all the way. This is another one of those. So, derivative of the first part, what is it? 2x. All right, we're off to a brand new marker.
Ew.
That didn't help things. All right, how about this? Hey, there we go. 2x. And original second part? All right, so we got d first times original second. Then we add to that what? Not yet. Original first, and then chain. Now for chain, let's think about the inside. What's the derivative of the inside part? 2x plus 2y dy dx. So that's d in. And then d out is going to be 3 times x squared plus y squared to be second. So this bit here is d out. So that's the derivative on the left side. On the right side, y squared becomes what? 2y dy dx. All right, at least on the right side, it's not terrible. Now, if you look at this whole d in, d out stuff, the whole second half of the left side, it's a bit yuck. You've got an x squared times a thing times a 3 times a thing squared. Let's distribute the 3. What can the 3 multiply? Well, you know what? Let's just multiply the 3 to the x squared and not even worry about distributing through here. So what I'm going to have us do is try to distribute as little as possible out. Because what with the exponents, distributing this out would be really, really terrible. So let's try to do as little distribution as possible. So we'll just take this 3 that's outside the thing squared and just put it on the x squared out front of that term. Things escalated a little bit like we're on. And now, what we want to do is we want to like figure out this is fine. This has to be distributed out a little bit, but we don't want to go whole hog and distribute it out like all the way with the x squared plus y squared all squared, and then multiply that to 2x plus 2y dy dx, and then multiply all that to the 3x squared. You don't want to do that. So what we're going to do is we're going to take the 3x squared and the 2x, and you know what? We're probably going to have to distribute the 3x squared through here. But then once we do that, we'll take this term and just slap it in front of these parentheses. And then we'll take this other term and slap it in front of these parentheses. But we're not going to like fully distribute stuff out. So we're not going to FOIL. We're just going to take term multiplied to the front of this and other term multiplied to the front of this. So let's distribute the 3x squared through a little bit. So we have 3x squared times 2x is 6x to the third. And 3x squared times 2y is 6x squared y dy dx. And all of that is multiplying your x squared plus y squared all squared. That just stays, and this just stays. And then 6x cubed is multiplying this thing. So we'll say, all right, 6x cubed times that thing, x squared plus y squared squared. Cool? And we're not going to FOIL that out and everything. It's just going to be like that. And same thing with the 6x squared y. We have 6x squared y dy dx multiplied to the x squared plus y squared squared. So we're trying to distribute stuff out the bare minimum to avoid having to do like this exponent all the way out and having like a million terms running across the board. Because as is, we already have more terms than we really want to do. So at this point, we are all distributed out as much as we're going to get. And you can now go into your like mode of getting all the dy dx things together. So where's the best place to get the dy dx stuff? On the right, because you already have some of that on the right, and there's no non-dy dx stuff over here, so just pick up this whole term, whoop, flip them over here, plop, make them negative. So those first two terms on the left are good where they are. So they're going to stay put. And then you're going to pick up that whole dy dx term and move it to the right side and make it subtraction. So we have minus 6x squared y dy dx, quantity x squared plus y squared squared. Now, at any point you can hit, hey, time out, and like we'll talk about stuff. From here to here, here to here, here to here. Okay. What happened? I distributed a little bit, but not all the way. So you see how we have like the x squared plus y squared all squared? We're trying to do this without multiplying that all out and going like x to the fourth plus 2x squared y squared plus y to the fourth. And then multiplying that to all this stuff. So instead, what I'm saying is let's take the 6x cubed and multiply it to the front of this factor. So we have 6x cubed times that factor. And then take the 6x squared y dy dx and multiply it to this factor. So we have the 6x squared y dy dx times that factor. And then we just say, and that's good enough. Those will be our terms. And we don't want to go crazy distributing everything out. The term out front just stays, the 2x quantity x squared plus y squared cubed. And the 2y dy dx on the right side just enjoying the show. Now, on the right side, what does everybody have that we care about? dy dx. You might say, also a 2y. We don't care about that. We only care about the dy dx. So you pull out a dy dx, you leave behind a 2y, and you leave behind a minus 6x squared y times x squared plus y squared squared. And then what do you do with that mess? Just divide the whole thing over. Meanwhile, this stuff does nothing. So all this non-dy dx stuff, once it's isolated, he just sits there and waits to get divided by something. So we end up with dy dx equals all that non-dy dx stuff just sitting there. So 2x quantity x squared plus y squared cubed plus 6x cubed times x squared plus y squared squared. So that just gets copied and pasted. And then you divide by this mess after dy dx underneath that. So you have 2y minus 6x squared times the quantity x squared plus y squared squared. And that's it. Well, we can reduce it a little bit. Ryan.
They're also 1x squared, like 6x squared.
Yep. Thank you. 4 point. So if you wanted to, like, I'm going to reduce this to simplest form, then everybody can be divided by what? 2. So you can say, all right, divide everybody by 2, so you get 1x and 1y, and then that 6 turns into 3x cubed, and this 6 turns into 3x squared y. And that is as simplified as it's going to get. Which first x? That one? I think that was this x, so I don't think so. No, because that's this, that. So no, that's not. It was, but we divided everybody by 2 to simplify. So originally it was a 2 and a 6 and a 2 and a 6. We divided everything by 2 to simplify the simplest form, and that's the only thing you can do to reduce this. Nothing on this quiz will be this level of like, this is far beyond anything on the quiz in terms of, like, the level of yuck. So everything on the quiz, by comparison, will be a lot less involved. Let's do one whiteboard problem, and then we're out of here. That took longer than I expected. What? Oh, yeah. The paper is extra fun practice. There's an answer key posted on Schoology, so I put that worksheet and the key at the top of the folder. And that's just, if you need more implicit differentiation in your life, you can do that. But I'm not going to look at or collect that evidence. All right, so one whiteboard problem. Say you have 3x squared y minus x equals y. And just get dy dx method. And when we're done, you're just going to leave your whiteboards and markers and everything where they are, because I'm anticipating using those in my blocks 2 and 3 today. Make sure you use product tool on that first part. Give me a second. Yes. That should be a plus 6xy when you do your initial step. And then, so at the very end, one of your signs somewhere in that fraction should be a positive or it's negative. That's good. Don't forget when you factor out the dy dx, that that's a 1 minus 3x squared behind. So here, when you factor out the common factor of dy dx, it's not just negative 3x squared, it's 1 minus that. Yeah, that's good, that's good, that's good, that's good. Very nice. You did the same things too. So when you go to factor out the dy dx, you got to bring this over, factor out dy dx, there's a 1 minus 3x squared.
I was right. I did the
That's good. So you're pretty close. You're almost there. That's almost good. That should be a positive 1 on the bottom. You're missing a 1 minus 3x squared. So, product rule. Derivative of the first is 6x times the original second is y. Original first is 3x squared times the derivative of second is 2 dy dx. Derivative of x is 1. Derivative of y is dy dx. First step, you're okay? Then, get all the dy dx things together. So I'll leave the 6xy minus 1 where they are. I'll leave the dy dx where he is, and I'll subtract over the 3x squared dy dx. Then, what I think is the most common mistake I'm seeing is that when we factor out the dy dx here, what's left behind? 1 minus 3x squared. A lot of us are forgetting that 1. So this dy dx, when you pull it away from itself, you're left with a 1, not nothing. So when you divide, you end up with 6xy minus 1 over 1 minus 3x squared. Or some of you have negative 6xy plus 1 and negative 1 plus 3x squared, depending on like how you got things across the equal sign where you put stuff. So either of these is fine, or if you want to rearrange things, 1 minus 6xy over 3x squared minus 1, that's also fine. You have homework tonight, more practice with your implicit differentiation tomorrow. Go over homework, do more review, more time on the whiteboards tomorrow, and quiz Thursday. Sound good? Sure. See ya. No bells today for the AP test.
How did you get the
This thing is from the quotient rule. So I'm starting here. This guy's derivative is the second derivative. And then quotient rule is low is y. Derivative of the high part is negative 1. Minus the high part is negative x. The derivative of the low part, derivative of y is dy dx. Over low is the bottom squared.
Oh.
So all this is just your quotient rule, filling in the pieces. And why is this y squared? Because when we replace dy dx with negative x over y, and we have this fraction in the numerator, we multiply by this fancy 1 to kill off that little denominator. So we multiply this to the whole numerator. Negative y times y is negative y squared. And negative y times the second part cancels those out and leaves us with negative x squared.
Okay, so why did you
Hi, Tess.